Hello, for today's class of Data Communications and Network 1, we'll talk about Chapter 5, Error Detection and Correction. This is Lecture 10, okay? And this is the Part 1 of Chapter 5. Okay. Error detection and correction is in the second layer, okay? It's the data link layer of the OSI model. Okay. Now, in order to talk about the error detection and the correction, we have to know the type of errors first, okay? What are the type of the errors? An error can occur, okay, when the received bit is not the same as the transmitted bit. So if you send something and the receiver receives something that is not the same as what you are sending, okay, it means that an error occurs. If the bit binary 1, okay, or bit 1 is transmitted, but the receiver thinks that the bit 0 was transmitted, and so it's like the binary 0 is received, okay? So send 1, receive 0, or send 0, receive 1, okay? We call this an error. So suppose we send something like this, okay? You can see that the green, okay, the green bit, okay, is the one that is wrong. So from 1 to 0 or from 0 to 1, this is wrong, okay? If you have a lot of bits that are wrong close to each other, we call this a burst error, okay? This is a burst error of length 10 from the 3rd bit to the 13th bit, okay? So it doesn't have to be wrong for every bit in the burst length, but if a lot of them are wrong close together, it's called a burst error. If one of bit is wrong, okay, apart from the others, it's called a single bit error, okay? This is a single bit error. So there are the type of errors we can, in the communications, we can think of it as single bit error and burst error, okay? And the code is used in order to correct both the single bit error and the burst error. The single bit error are isolated error, and usually it occurs from white noise. But the burst errors are usually occur from impulse noise and from the fading effect, okay, in wireless channel. Now we have to define the error detection and error correction. Error detection means that the receiver knows something is wrong, okay, but it cannot correct. It cannot do anything. It can just tell, okay, maybe alarm or show that this received sequence is wrong, but it cannot correct it. Okay, so this is error detection. Know something is wrong. Okay, error correction means that you know when something is wrong and you can also correct it. You can correct and make it right. Okay. Now let's look at error detection process. At the transmitter, first you have k-bit data. Okay. Then you calculate from the data, okay, to have the parity check bits, okay, n minus k bits here by some function. For example, you may use odd parity, okay, odd parity bit, okay, which means that you count the number of ones in the data part, and you make the whole code word sequence, the n bits, okay, to have an odd number of ones. So if, for example, if the data part have 10 bits of ones, okay, you will add another bit at the end, another one at the end, so it becomes 11 bits, which is an odd number. But if the data part has 9 bits of ones, then it's already odd, okay? So the bit that you add at the end, it will be 0, so that the total number of ones is still an odd number, okay, in the n bits. Then the transmitter will transmit the n bit code word, okay, to the receiver, and the receiver will, when it gets the data, okay, the data doesn't have to be the same as the data that was transmitted due to noise and the interference and the distortion in the channel. So we say data pram, okay, you can see that it's data pram, it's not the data. And then the same function was done at the receiver. So receiver calculate what should be the parity check bits, okay, at the end. That should be added into the data to become a code word. And then it will compare to the received parity check bits, whether it's the same or not. If it's the same, then there's no error detected. But if it's not, it means that it detects some errors. Okay? Again, you can see that EPROM and data prom, okay, they are not the same as at the transmitter. That is just the E and the data, because the received data may be different from the transmitted data. Okay, this is as what I just told you. The parity check is the easiest error detection scheme. Okay, and you use n minus k equal to 1 bit to check the data, and we call this one parity check bit. We can choose whether we use an even parity detection or an odd even parity detection. The even parity detection means that the number of ones in the data plus the parity check bit must be an even number. Okay, so if you want to know two additions of the ones in the data and the parity, it has to be 0. If it's not 0, then you need to check the error. For the odd parity, we have already talked about. In this case, if you want to load two additions of the ones in the data and the parity, you have to have a result of 1 to have no error detected. The second case is linear block code. Okay, for linear block code, you have the data and the check similar to what you have in the parity check code, but in this case, you usually add more than 1 bit, okay, of the n minus k, and you have, and sometimes you don't add at the end, but you may change the data into the code word, okay. So the basic one, the one that we usually use is that we add the n minus k bit at the end, okay, but not necessarily to do that. So if you have k bit data coming in, and then you go to the FEC. FEC is forward error correcting encoder, okay, and then you change the data into the code word, which is n bits, okay, and then you transmit it to the receiver. The receiver receives the code word, okay, and it will go to the FEC decoder. So the forward error correcting decoder will look at the code word, okay, and compute, okay, whether there is an error in the code word or not. If there is no error, it will give out the data, or if there is error, there are errors, but the FEC decoder can correct it. It will correct and give to data and give out as a data. But if it's something that is detectable but not correctable, okay, which means that it knows that something is wrong but it cannot correct, then it will send out as uncorrectable error. So the receiver will know, the user will know that this cannot be used. Okay, this is not correct. So the difference between the error detection process previously and error correction process in this picture is that the error correction code is more complex than the error detection code. Okay, because you have to be able to correct the wrong symbol values or the wrong bit values to correct bit values. Now, to consider about the error correcting code, okay, or error detecting code, we have to think about the probabilities, okay, of how much it can correct or how much of the error can happen, okay, can occur. So we will look at this. We have the P sub B is the probability of a single bit error. Sometimes we call it a bit error rate or the BER, okay. So we assume that the errors are independent, okay. This is the easiest case. So if you send a frame, for example, a frame of n bits, okay. So you have a sequence of n bits, okay. And then if there is no error for the whole sequence, okay, you call this one probability P1, that there is no error, everything is correct. And this is one case, one event. Another event is that there are errors. When there are errors, there are two different cases that can happen. That the error is undetected, okay, which is P2. This is the probability that error occurs, but the decoder cannot, or the receiver cannot detect the error. And the other case is error is detected, which is P sub 3. In this case, the error occurs and the receiver or the decoder knows that something is wrong. Okay, so the probability of these three cases have to be 1, right? P1 plus P2 plus P3 has to be 1 because these are all the cases that can happen. Okay, and the P1 that nothing is wrong. If you have n bits, you have to be 1 minus P sub b. Okay, for every bit. Okay, because P sub b is a pop that 1 bit is wrong. So 1 minus P sub b is a pop that 1 bit is not wrong. Okay, that this 1 bit is correct. So if you have n bits, okay, and every bit have to be correct, you have to multiply the probability that 1 bit is correct to all of the bits. Okay, so you will have 1 minus P to the b, 1 minus P sub b, okay, and the total of them to the n. If there is no error detection, okay, no check bit at all, you cannot detect. Okay, so P sub 3 is 0, and P sub 1 is equal to 1 minus, P sub 2 equal to 1 minus P sub 1, which means that all the errors go undetected. However, if error detection is used, then almost all of the errors can be detected, and P sub 2 is very, very small, the undetected error, if you use good codes, okay? The undetected error is small. So the probability that you cannot detect the error is very small. So P sub 3 is approximately equal to 1 minus P sub 1. Okay, so this is what we want, okay, that almost all of the error can be detected. The code that have been used a lot, okay, is called Cyclic Code, okay, Cyclic Redundancy Checks, or Cyclic Code, or CRC, okay. This is one of the most common and powerful error detecting and correcting codes. If you have k-bit box of bits, okay, and the transmitter will generate the n minus k bit sequence, okay, which is we call the frame check sequence or parity check bits, okay, and attached to the data. The frame check sequence, okay, is chosen so that the transmitted frame or code word, okay, which is n bit long, is exactly divisible by some predetermined number, which we call generator sequence. So you have to think about this. If you want to know that what you receive is correct or not, you have to have some means to check it, okay? And the cyclic redundancy check or cyclic code use the method that the code word, all code word has to be divisible by some sequence, which we call generator sequence. If it's not divisible, if the data is not divisible, it have to add the n minus k bits at the end, or the frame check sequence, or the parity check bits, okay, at the end, so that the total code word is divisible, okay. Then at the receiver will just receive the sequence, right, and it will divide by this predetermined sequence or the generator sequence. If it is divisible, okay, there is no remainder. This is a code word, okay, and it will assume that no errors occur, okay, and this is correct. What you receive is correct. But if it's not divisible, there is some remainder, then it will assume that, it will know that error occurs, okay. It always knows that error occurs if the remainder is not 0. But if the remainder is 0, I say it assumes that it's correct because this is the best that it can do. It is possible that even though it is a code word, it is not a code word that the transmitter transmits, okay? Because the transmitter transmits a lot of, you know, there are all possible code words that can be transmitted. It's possible that the error just changed one code word to look like another code word. In this case, it becomes undetected error. However, if you use good cyclic code, okay, then most of the error goes detected, okay, you can correct, so no problem in that case. So if remainder is 0, you say no error, the decoder say no error. If remainder is not 0, then there are errors. Okay, so now how to find the values of the frame check sequence or the parity check sequence. Okay, there are 3 ways to compute this, to find this. Okay, first, using multiple choice arithmetic. Second, use polynomials. Actually, the first and the second case, they are similar. Okay. The third is the digital logic. Okay, by using chip register circuit. Okay, you can use hardware to do this. Now, for the first one, the modulo 2 arithmetic. Okay, you have to know modulo 2 first. The modulo 2 is the same as exclusive OR operation. Okay, or the XOR gate in the digital logic design. So in this case, the modulo 2 arithmetic is the same as addition and subtraction of binary with no carries. So if you look at the table here, 0 plus 0, okay, modulo 2, okay, becomes 0. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. So the one that is different from the usual case of the addition is that 1 plus 1 is 0 because we don't keep the carry. So this is an example, 1011 plus 1101, you get 0110, okay? Because there is no carry, 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, okay? Now let's look at to find the values of the FCS, okay, using the modulo 2 arithmetic, okay? How to do this, okay? This can be done by adding n minus k bits of zeros at the end of the message sequence and divided by the generator sequence. Okay? The remainder of this division is the FCS. So this is the method to find it. But why does this work? Okay? So to see why it works, that you add n minus k bits zeros, okay, at the end of the message and then divide it by generator sequence. And the remainder is just the FCS. So how can we know that this works? So look at this formula. Okay, this is to prove that why this method works. Suppose FCS. Okay, if the remainder. Okay, this is the formula. Okay, the FCS is the remainder of 2 to the n minus k multiplied by vector u. Vector u is the input data. Okay, in vector form. So if you multiply by 2, it's like you shift by 1 to the left, okay, and add 0. For example, if u is, to think of this, if u is 110, okay, you multiply by 2, you get 1100, something like that, okay, because 110 is 6, right? So you multiply by 2, you get 12, okay, so you get 1100, which is 12. Okay, so when you multiply by 2 to the 1, it's like you shift the sequence to the left by 1 position, by 1 bit. If you multiply by 2 to the 3 or 2 cube, you shift by 3 bits. Okay, so this is like shifting and then divided by the generator sequence. Okay, so this is the method to find the remainder. We will look at an example later. This is a proof why the equation is correct. We define V is the n-bit frame to be transmitted. Okay, we call this code word. And U is the k-bit message. Okay, we call this message. Okay, and B is the n minus k bit. We call this check bits. And the G is the pattern of the n minus k plus 1 bits. Okay, this is called generator sequence. This book use the textbook use different notation that I'm using. Okay. Because I'm following another text, okay, which is Error Control Coding by Lin and Costello, which is kind of the very important book in channel coding. Anyway, we can express the code word, okay, in terms of the message and check bits, okay. So the code word is what? It's 2 to the n minus k times u plus b, okay. What is this? Let me show you. Okay, so this is like shifting the sequence to the left. Okay, so for example, if u is equal to 110, then 2 cube multiplied by u equal to 110000. Okay, something like this. Okay, so add 3 zeros. Okay, as the n minus k. Then you want the v, okay, to be divisible exactly by g, which with no remainder, okay. So you divide it by g equal to it's like divided this by g, right? Then this one, okay, this one is just kind of a sequence divided by a sequence. If you have a number divided by another number, you can have a quotient and a remainder, okay? You can always, for example, you have 7 divided by 3, you can have 2, and with this is quotient, and you have 1 as a remainder. Okay, so this can also be written as a quotient and a remainder. Okay, so this one can equal to Q quotient plus this is the remainder. Okay, so from 7 over 3 divided by 3 is 2 with a remainder of 1. This 7 over 3 equal to 2 plus 1 over 3, right? So we can written as this, okay? This is the remainder, this is the quotient. Okay, so this is a remainder and this is the quotient. So you have the formula look like this. It's a sequence or a vector, so I put a sequence, a vector symbols here. Okay, now you have a quotient here, and this is you have A over G plus B over G. Now you want V over divided V by G to be no remainder. So this is quotient. Then you want the remainder to be 0, right? Remainder go to 0 because you want this to be exactly divisible with no remainder. To have this one equal to 0 means that A equal to B. Because if A equal to B, you will have A plus B over G equal to 0 because A and B is equal. And if you remember, this is a sequence of binary, okay? And you add with modulo 2. This is add with modulo 2. So you have, for example, A is 1, 1, 0, B is 1, 1, 0, you have 0, 0, 0. Okay, so you have to select A equal to B. Or the B equal to A. Now, so from this is what we know, right? We know because we received, and we multiply by the number of bits that you want to add as the number of parity check bits, okay? We want to find B. Now, how to find B? B has to be equal to A, right? B equal to A, then what is A? A is, get it from, how can you get A? You get A from the A equal remainder of 2 to the n minus k multiplied by u divided by g, right? From this one is the remainder of this one is A. So B also have to equal to this, okay? B have to equal to this, and that's why we get the check sequence to be the remainder of this, okay? This how you get this. Okay, this is the check sequence is equal to remainder of 2 to the n minus k multiplied by u divided by g. Okay, now let's look at the. Okay, so this is what I just showed you in the sheet. Let's look at an encoding examples. Okay, to encode means that you have a message, and then you have a message coming in, and you give out the code word, okay, encoder. You have a message coming in. You give out V code word. So U is this, okay? So V is like you have to add n minus k bits, okay? So this is data. This is data. This is n minus k bits, okay? So look at this example. You have a message, okay? U is 1110. So you have k bits. K equal to 4 bits, okay? Data. And the generator sequence, okay? Generator sequence of the code that we are using. Okay, for different code, we have different general sequence, okay? In this case, we use G as a 1011, which is the size of G is equal to n minus k plus 1 bits, okay, which is 4 bits. This means that the check sequence has a length of 3, okay? So this is 3 bits, this is 4 bits, this is 3 bits, okay? So this is NK cyclic code equal to 7, okay, because total is 7 bits, okay, and K is 4. So this is 7-4 codes, okay, and different code has different generator sequence, okay, even though it's the same length, okay, you can have different generator sequence. And the general sequence, how to find it is above the scope, this course. So if you want, okay, you can take another class, and I'm teaching the 01-205-525 channel coding theory. Okay. Anyway, you want to check to find the remainder and and the code word V. So to find the remainder, okay, first you have to ship it. Okay, you have to ship the U. Okay. Because you have to find this, right? You find the check sequence, okay? Remainder of, now n minus k equal to 3, so 2 cubed multiplied by U, and then divided by G, okay? Divided by G. So when you multiply 2 cubed by U, you get 1110, and you add another 3 zeros, okay? So you have 1110 and then 000. Then you divide the chip that U, okay, with the generator sequence with 1011. Now, how to divide this? Okay, I will show you. Okay, so first, when you want to divide this, you got 1, right? So this is 1011, right? Now, when you add, you do modulo 2 arithmetic. Modulo 2, okay? Arithmetic. Modulo 2 arithmetic means that if it's the same, it becomes 0. If it's different, it's 1, right? So plus or minus is the same. So 0 and 1 is 1. This is 0. This is 1. This is 0. Okay. So you get 101. Okay. To divide further, you have to take this one down. So 1010. So 1 again. 1011. So you get 1. Okay. This is 000. Okay. You don't have to write that. So you take another 2 zeros down. You get 00. Now this is 3 bit, this is 4 bit. You cannot divide further. Okay? So this is the remainder. Okay? We don't care about the quotient. Okay? We don't care about the quotient. We just care about the remainder. The remainder is the n minus k bit that you add. So the data is 1110. This is data. Okay, and then you add 100. This is the check bits. From this is equal to code word V. Okay, so you can see in here the frame check sequence is b equal to 100, so the code word, as I just told you, 101, 1110, and then 100. Okay, the first part is the shifted data, and the right part is the FCS, or the check bits. The second one is the second method to find the frame check sequence or the parity check bits, okay, is similar to the first case, but instead of using just the binary values, we put it into the coefficient of polynomials, okay. So sometimes some people are more comfortable using the polynomials, okay, instead of a sequence of 0 and 1. So again, we will write the code word V, the data U, the parity check bits B sequence, okay, and G, the generator sequence, as in polynomial form, okay, with the dummy variable X. So the message will be from vector U equal to UK minus 1, UK minus 2 into to U sub 0, okay. You put it in the polynomial form using the values of the bits, okay, as the coefficient, okay. So you get, for example, U equal to 1110, 101. The left-hand side, the leftmost side, is the most significant bit, okay. So the most significant bit will correspond to the highest degree of x. So ux, the polynomial of the message, is equal to x to the 6th plus x to the 5th plus x to the 4th. We don't have x cubed because at that position, at that bit, okay, x cubed is 0, the coefficient is 0. Then you have x squared, you don't have x because coefficient is 0, and you have plus 1, okay, x to the 0 is 1. So in this form, we have code word, okay, similar to the binary case, okay, but however, we instead of multiply by 2 to the n minus k, we multiply by x to the n minus k, because x to the n minus k is how you shift the term, okay, of ux, okay, to the left. Again, you still find the remainder by you still have to find the remainder of x to the n minus k u of x over divided by g of x, okay, to get the frame check sequence. Let's look at another examples. You have n equal to 7, n minus k equal to 3. Ux is x cubed plus x squared plus x, okay, and gx is like this. To find the remainder, you divide. First, you shift ux, okay, by multiply by x to the n minus k. In this case, n minus k is equal to 3. So you multiply ux by x to the x cubed, and you get x to the 6th plus x to the 6th. Sorry, x to the 6th plus x to the 5th plus x to the 4th, okay? I will show you how to divide this in the paper here, step by step, okay? So you have x to the 6th plus x to the 5th plus x 4th. This is x to the n minus k multiplied by ux, okay? And you have x squared, x to the cube plus x plus 1. This is gx, okay? You always have to put the highest degree, okay, on the left, okay, like this to divide. So to divide x to the 6 by x cubed, you get x cubed, okay? X to the 6th plus x to the 4th plus x to the x cubed, okay? Again, this addition is the modulo 2 arithmetic. Modulo 2, okay? So all of these are modulo 2. So x and x to the 6 plus x to the 6 is 0, okay? This one you get x to the 5th. This is 0. You get x to the x cubed like this. Then you divide further. You multiply x squared to x cubed, so you get x to the 5th, okay? Plus x cubed plus x squared. Now you get x squared. You see that this is degree 3. This is degree 2. So you cannot divide further. This is the remainder. Okay. So Vx is what? Is the data here that is shipped already. Okay, plus remainder. FCS. Okay, this is the code word. And in binary format, this is x to the 6th to the 5th to the 4th square, x cubed, you don't have x square. And you don't have x and x to the 0, okay? So this is data frame check sequence, and this is the code word in binary form, okay? Okay, you can see the code word in binary form. This is similar, it's actually the same as the code word in this case, okay? It's the same example, but we find the frame check sequence to get the code word using the binary format and using the polynomial format. Okay, now the next, so this is the end of this tape, and the next tape we will talk about the chip register circuit, okay? And we'll see the encoding by chip register circuit, and we'll talk about how to decode, okay, and how to correct the data. Okay, so thank you.